So this tonight we're going to any question? Oh yeah, do we have any questions? No. Yes, yes means I don't know. What does it mean by yes? Yeah, Shafiq. Hello, hello. Oh no 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 no. So tonight we'll try to do like a dynamic simulation in HYSYS. Just to give a brief overview. So I think I can just better draw it because I still cannot open my Dropbox and take some time as well. A minute there. So what we have learned last time, let me check. Come on. Well, in any case, so so let me just draw it here. So what we have learned so far is then the steady state, what we call it steady state. And then in the steady state there is no accumulations, and then in our chemical engineering we know that we have if for example if we have a box, a process, and then we have the materials coming in like a flow rate of a flow meter, and then we have materials going out, and this then F1 and this then F2, and we also have another stream going out, so we call this F3. And then in steady state, yeah, in steady state, so we have F1 equals to F2 plus F3, right? And then if we know F1 and then we know F2, obviously we can calculate F3. Yeah, so we have one equations, three unknowns. So if we know two variables, that means we can calculate the third variable. So the degree of freedom is two, basically what we see here for the steady state. But then and then we also see yeah, for this example, so for example if we have a vessel, so if this then the vessel, and then you put a valve here, and then you put a valve over there maybe, and then you put like I don't know, a valve over here, and then you can always see, yeah, in steady state that F1 should be equals to F2 and then plus F3. Yeah, so this is what we have in steady state. um, and then in dynamic, yeah, before we start, in dynamic, so we have the same box, and then we have F1, we have F1, and then we have F2, and then we have F3, F3, and then in dynamic we have what is then coming in. So F1 here is that's a mass, yeah, it's kilogram per hour, for example, and then it has to be equals to F2, right? And then plus F3, F2 plus F3, yeah. So F1, what is coming in, equals to F2 plus F3. So all of this in kilogram per hour, like what we had in our steady state. But in dynamic, we need to see something that is changing in time, yeah. For example, in this case, if we have like a mass coming in, and then we would like to see what is then the mass accumulation in here. So we can call this like a dm dt. Okay, so if we have like huge flow rates coming in the F, oh sorry, I thought you could see it. Share screen. Start sharing. Can you see anything? And then I have to redo this again. Yeah. Yeah. Okay. Anyhow, I can just use the same screen. Dynamic versus steady state. Okay. Where's my pen? Oh, this is my pen. So we have a vessel, for example, yeah, we have a vessel, and then as I mentioned before, so we have incoming flow rate, and then we have outgoing flow rate, and then F2, and then another outgoing flow rate F3. So F1 is then the any mass flow rate, so kilogram per hour, for example, and this also kilogram per hour, and this also kilogram per hour. And then we know that F1 equals to F2 plus F3. Yeah, so this is then the expression in steady state. But the actual expression is that we have, if we have like F1 coming in a lot, right? And then we have F2, we close the valve, for example, we close it over here, and then we also close the valve over here, 3. So that means if we have F1, there is a value in F1, but there is no value in F2, and there is also no value in F3. That means we will see the level over here, right? The dm dt will be increasing as well. So you imagine that you have a bathtub, and then you are filling your bathtub with water, but you are closing the outlet of the bathtub, right? So in this case, you are filling in the tank or the bathtub. So in this case, if we have like a F1 should be equals to F2 plus F3, and then we have here plus dm dt. You can imagine now, yeah? So if we have F1 for example, equals to 10, and then F2 equals to 0, and then F3 equals to 0, that means dm dt is 10. It has to be 10. Yeah, and then if F1 is then 10, and then F2 is then 2, and then F3 is then 3, and then dm dt should be 5 in this case, right? So we can see, but then if we have like F1 equals to 10, and then F2 equals to 5, and then F3 is also equals to 5, that means this one is going to be 0. But then in another scenario that we can have also, the F1 equals to 10, same, and then F2 equals to 6, and then F3 equals to 5, and then this has to be minus 1. Can you follow? Yeah, so that means in this case we have a positive dm dt, so the level increases by 10, and this also the level increases but by 5, not so steep like this, but I will draw it a little bit like that. But this one, the accumulation is 0, so it will be like a 0. This one, accumulations is negative, so it will be pointing downward. So from here, what we typically use is that dm dt equals to what is coming in, which is the F1, what is coming in, yeah, and then minus what is coming out, which is then F2 plus F3. So what we have then typically is then accumulation in chemical engineering equals to in minus out. So this is then the general formula for the dynamic. So these accumulations, in our case, it's a mass, but in other case, it could be mass, it could be heat. Yeah, it could be heat, which is defined by the temperature, and it's also like a pressure. Yeah, it can also be height, liquids level. So you will have like in this case you have dm dt. You could also have dt dt, and you could also have dp dt, or the HDT, and so on and so forth, etc. What causes the MDT to be negative? What causes the MDT to be negative? For example, this one. For mathematically, it can be negative. If you have more outgoing. So here we have incoming is then 10, and then the outgoing is then 11, and then your accumulation should be minus 1. right? So in this particular case, now you have a vessel and you have a bathtub, and then this is then the F110, and then you have it's evaporating, for example, it's a 5, and then this is then the 6. So you had this level, but then if you have this, and then this level will drop by -1. Yeah, so in this case, for example, you have a flow rate coming in fixed, and then it's the vapor. For example, this may be two-phase flow, and then you have a vapor coming out 5, but then you open the valve very big, and then you have a higher flow here 6, and then the level in the tank should be then reduced by -1. Okay, any other question? Because this one you have to understand this very clearly. Yeah, so um okay, and then I think let me see if I can if I have already my method file. Let me check, yeah, if this is the updated one. But now at least I hope you understand what the dynamic and steady state is all about. I think I made this slide. Yeah. I've mentioned to you this, which is the easiest one. Yeah, this is the easiest concept that I can think to explain to you. So we have a steady state F in equals to out. Yeah, what we saw already, and then dynamic is then accumulations equals to in minus out. And then this is also like this that's what I just mentioned. So in steady state there's only like one equations, but in dynamic you could make all kinds of equations. So you can see the pressure profile in the system, you can see the concentration or the mass profile in the system, you can also see the temperature profile in the systems. Yeah, so if we can learn something about this types of phenomena, it's about momentum, mass, and then heat. So momentum, mass, and then heat, we have everything here covered in the dynamic simulations. To give a feeling on how dynamic simulation compared to the steady state. So in steady state, you have only like one equations. F1 equals to F2 plus F3. There's nothing more. There's nothing more. Yeah, it has to be the same. So like in this case, so if we have in this case, I think where's my pen? I don't know where my pen is. Oh, this one is my pen. So so this part, yeah, you can see this. So coming in is 10, but it's coming out is also 10. Yeah, 5 plus 5, and then the mdt equals to 0. So when this dmdt, when the accumulation equals to 0, this is what we call as steady state, because in this case f1 equals to f2 plus f3. Clear? Yeah, it could also be like a 6 plus 4. Yeah, as long as this is 3 or plus 7, as long as the dmdt equals to 0, and then you have a fixed flow rate over here, and then you get what we know as steady state situations. So that's basically what the steady state is. So if we would like to compare this with the dynamic. So in dynamic, so we have I think I have a pen pen. Is it pen? No, no pen. I don't know where pen is, but in any case, so we have you have seen this, yeah? Accumulation is equals to in minus out, and then we know these accumulations dvdt, yeah, because this is a volumetric flow rate. For example, this is meter cubic per hour, and this has to be also meter cubic per hour. But yeah, meter cubic per hour, but I just want to see what the height of the column, what the height in the vessel is. So volume equals to area, the area multiplied by the level in the tank. Yeah, so the area is fixed, level is constant. So we have area and then h, and then area is also like 1/4 pi and then d square. Okay, and then we can then plug this into A, and then plug this times H, and then you plug it over there, F. Okay, and then the F out is then this F out depends on the pressure drop over here. yeah, which is then the CV, and that it also depends on the delta P. So we have to specify what the pressure here, what is then the pressure here. So depending on the difference between this and that pressure, and then the valve coefficients, we get the F out. Okay, and then this pressure over here, yeah, it could also be the same, because if this is then atmospheric, that's also atmospheric. So that means the pressure over here is then rho GH, so the delta H over here, and then delta H is then the H minus H0, or H. So H0 is just H0, make it like a zero. So H, we have H. So we plug all of these numbers. So we plug it, and then we get this. Put it over there, and then because diameter is constant, yeah, diameter is constant, but the height can be up and down, and then we have dH dt, and then equals to F in. Yeah, there is no, we don't, at this point in time, we don't have any substitution for F in, but for F out, we know that we have the CV square root of delta P, while delta P is then rho G delta H. Yeah, this should be delta H, and then you do your magic, and then in the end you'll get delta H over dt. So these are all the equations used to describe one single vessel in a dynamic simulation. Yeah, so this is completely different than the simple steady state. Steady state is easy peasy. You can just one click and then it's done, calculate it. But then for the dynamic, it has to go all of these steps of calculations, so that in the end we know for every delta t what is then the delta H. Okay. um, and then in the simulation, any questions so far? No.
Yes, I do have a question.
Very good.
I like to ask, when do we apply dynamic simulation
ah
as opposed to steady?
Very good, very good. Dynamic, as we see, dynamic here, I put this always like so it's always, where's my pen? Oh, this is my pen. So it's always like a dm dt, dt dt, dp dt, and then dh dt. So the only thing that is common is then dt over here, dt, and then dt, and then dt. So it means that the mass changing in time, the temperature changing in time, the pressure changing in time, the h, the level changing in time. So if there is a change in time, and then we'll then do the dynamic simulations, means that means, for example, we have the same, we have this level, right, 0, and then we would like to know, yeah, with this flow rate that I have, and that outlet flow rate that I have, and this flow rate that I have, what is then the time, so that the level goes until this point, for example the 90%. How much time with the current flow rate of F1, F2, and F3, what time does it take for me to get to this level? Yeah. And then it's also the same case, for example, yeah, so for example, you have in this scenario, you have, for example, this valve is somehow blocked. Some idiots just close this valve, it's blocked. And also this valve is also blocked. Yeah, but you cannot close this, there is no such a valve, so it's just like coming from the upstream. And then because if this happens, yeah, if this happens, and then it could lead to, like, for example, a dangerous situations, I don't know, maybe there's leakage over here, I don't know, and then it has like a level over here. So you would like to know how much time do you have to get the level from here to fill up the complete tank. What is then the time required? Yeah, so in this
Yeah.
case we know that we have that the mdt equals to F in minus F out, right? So F out, we say that it's equals to 0, so it is going to be 0. So we have the mdt F1, and then here you can integrate that, yeah, dm equals to F1 dt, and then you integrate the m, integrate the f. So dm over here is, for example, this is another 50%, another 50%. So it's another 50% equals to f is a constant, for example, in this case, and then you can calculate that delta t. So what is then the delta t? So 50% divided by f. then you will get delta T. So that's basically how the dynamic calculation is done. In this case, you can also plot, because when we do the dynamic simulations, we can have a plot, temperature, and then in this case, for example, H, and then it has like a simple H0 initial H, and then because of the F1 is keep coming, F2, F3 is then 0, so it will then go up like a straight line, and then in here, for example, this then the H equals to 100%, and then we can then go here, and then what is then the time, the delta T over here, from here to there, what is the delta T? That is then the questions. So if someone asks you how fast the pressure changes, how fast can we remove the materials, how fast the temperature changes. If someone asks you how fast, means they are talking about time, means we have to do dynamic simulations, because we need to know what is then the time available for us to do something, or for something to happen. So it's about asking about time, how fast something can happen. That's when we have to do dynamic simulation. Let me know if that is not clear enough.
Is is clear.
It's clear or it's not clear yet?
Well, I just maybe if we are trying to simulate a
Yeah.
theoretical plan, so we will opt for steady state. And if we are trying to observe changes
Yeah.
over time, then we would opt for dynamic. And so dynamic is more applicable to like a real or realistic plan.
Most in realistic situation, it's just that if this then your plant, yeah, control N, so you have a plant, you can have a reactor, you can have column, you can have action, you have a pump, whatever. So we have coming, incoming, outgoing, and then if you see that F1 and then F2, and then there is no other F, for example F3, yeah, for example. So if you then get this reading, and then get this reading, and get this reading, and then you can see F1 is constant. So we have and then this is time, this is F, whatever F, and you can see that this is then F1 goes constant, and then for example this is also F2, 2, something like that, and then you can see also obviously this is then F3 here. So if they don't change in time, they are considered as steady state. But this is not going to happen in practice. What will happen in practice is typically something like this. Hmm. So it's somewhat changing in time, but overall you could see like there is a constant, roughly a constant number of F1, constant number of F2, constant number of F3. So in this particular case, your plant is in steady state mode. But say something, like for example, yeah, say something, some people just, for example, this goes to another plant or another equipment, for example, and then this is then closed, right? So if this is closed, so this becomes 0, and this is then always 10, and then this one, where's my pen? This one, it was, for example, it was 5 and 5, but then since this is closed, this becomes 0, and this can either start to go like 6, 7, 8, and so on and so forth, or until 10, yeah, until 10. This could also be the case, or they have a limitation. For example, they have limitations in the pipeline, or there's a valve over here, or there's some requirements, so they can only go until 6, for example. Yeah. So if this can go until 6, so that means there should be like an accumulations of the material somewhere in the plant. And then what we will see in this particular case is that, so we have F, and then we have this F1, it keeps going constant, right? 10. And then the F2 was this one, F2, but then suddenly it drops to 0. And then your F3, it was happy here, but then because this dropped to 0, it just increased a little bit, but then it cannot go any further. Yeah. So this we have constant incoming flow rate, 0 F2, but then F3 it has this number. So basically we are missing this flow rate. And then this you can see there should be an accumulations in the plant somewhere. So the DHDT somewhere or the MDT is increasing somewhere in the plant. Yeah, it has to be somewhere in the plant. So in this particular case, because we can see changes in the plant, so we can say that the plant is now in dynamic. I mean, it's in dynamically changing. And then if someone asks you, yeah, so now tell me what is then the time required for F3 from 5 to 6, for example. So he wants to know this timing, because then he or she can take action. So what is then the time? So if someone asks you to get him or her the time, and then for this you have to do dynamic simulation. Okay, so let's put this into practice. Yeah. So we have, for example, for easy, what we will draw is make another one. What we'll draw is simple. We have air plus water. So we have a valve, and then we have a vessel, and then we'll have the air will then go up, right? And then the water will then goes down over here. And in dynamic, it is advised, yeah, because you could do anything in simulations, but then in real life, the flow rate, the only thing that the flow is a function of delta P, yeah. If there is no pressure drop, that means there is no flow. But if there is a pressure drop, that means there is a flow. Okay, so just think of it in a highway. So you have a highway, and then you have a car over here, and then a car over there, and then a car over here, and then a car over there. So if there are so many cars on the road, that means you are moving slowly. Yes. Yeah. If there's so many cars on the road, that means you are increasing the resistance in the line. That means you are moving slowly. But say that you are now you have you you kill this guy, and then you shoot him dead, you shoot him this guy dead, this is dead, and then now you have only you yourself in the road, and then you can just drive 200 kilometers an hour, right? There's no restriction whatsoever. So um depends. So that's how the pressure flow works. So in here we have to specify the pressure source, and then we put a valve over here as well. And then here we have to say that the atmospheric pressure, for example. And then this is also like another atmospheric pressure, for example, or another pressure 3. This is pressure 2, for example, and we have to have a valve over here. Yeah. So depending on this pressure here, pressure there, and then pressure here, and then it will calculate for us how much is then the flow that goes into here, what is then the level, how much air goes up, and then how much liquid goes down. So that's basically what we will do, yeah, in this um, half an hour. In the meantime, if you have any other questions, let me know. Yeah. So we are going to do this in HYSYS. Let's do this. Open. You are opening your HYSYS file, yeah. Hello.
Yes.
If I'm moving too fast, let me know, yeah.
Okay.
If it's not clear, let me know. So let's say we just simple, yeah, make it water and then air, and then we will select for ideal gas and one, and that's it. Yeah, for this simple case. Um, so first is then we have to have a material stream. So what's easier now with this IC is that you can just put the main equipment. Like in this case, we have valve. So three valves and then one vessel. So in this case, we can also do the same. Valve one, two, three, and then vessel there. Looks like a tank. Delete, and then vessel. And then we can, in this case, we can easily send it there, send it over here, and then send it over there, send it over here, over there, and over here. Okay, so we just say I have like a 1000 kilogram an hour, or make it 10,000 kilogram an hour of fluoride, and then it's ambient temperature, and then 1 atmospheric. No, 1 atmospheric. We want to have it like a pressurized, so let's say that the 10 bar, and then the unit is very strange. So I'll just change it to SI, Euro SI unit. And then the composition is, let's make it 80% of water, and then the rest is then air. So we have two phase flow coming in. Yeah. So we have a volumetric flow rate of 10 meter cubic an hour in the ideal liquid flow, and it goes through a valve, and then in this valve we know that we have to specify the delta P, yeah, in this particular case. So you could specify, for example, I specify like at I don't know, maybe 1 bar, and then the results is then calculated, and then this vessel is there's a default already, yeah, as you know, there's a default uh, um, uh, input for these vessels in ISIS, and then we have the liquid coming in, sorry, liquid vapor coming in. For example, it's um, sea vapor is 2874 kilogram an hour, and then the remaining 7000 is then the water as we have defined it. So the 2874, it should coming out in the top, yeah, basically. So we see it's hopefully it's 2874, it's 2874, and then the liquid is then the remaining, which is then the 7000 something. And then in this case as well, we can specify the delta P as it is, yeah. Okay, for example, I don't know, maybe like a 4 bar, and then we can see that this outlet is 5 bar, yeah. So the outlet is 5 bar. I think I better show the table. Okay, and then this one as well, I can better show the table. Then I press home, and then this one as well, I have to specify the delta P. In this case it's also like a 4 bar, for example, and then we specify uh, we show the data. Okay, so we have let's make it add variable, and I would like to see the mass flow rate, yeah, because I don't like mole flow rate. Done. I'll just remove this more. 10,000. Double click here if you'd like to. You can just remove this and then add the variable. Uh, Done. And double click here and then remove this and then add another variable, and then the match flow right here. No, I have to click that and done. And that's it. Okay, so 10,000 to add 674 7126. So f1 equals to f2 plus f3. So this is then the steady state what we have been talking. Okay, so we have done with the steady state, and then in this case you can save it. You can save it somewhere, desktop for example. So I don't know, simple case. um so how to turn this into a dynamic simulations? When we go back here, I mentioned something about the DHDT somewhere. This one, in this case, if you see this, there is a diameter parameters, right? This is then the final equations, and then there's a diameter equations coming in. Sorry, diameter parameters coming in. 1/4 is a constant, pi is a constant, f1, fi is given, yeah, because this is something that we specify ourselves. And then this is also constant, and this is a parameters that we need to have in this vessel. And then g is a constant, density is also information that we can have from this guy. So if we can solve this like what we did over here, so we are solving this, that means we know what the density is. Sorry, but we have the CV as well. So this CV is also a parameter needed to be put into the valve. So basically this equipment, it has diameter, so that diameter is something that we have to specify. This equipment is also have a CV, it's also something that we have to specify. So in all is that all equipments in the unit operations, because it acts as an accumulation, yeah, it acts as an accumulations. Either it's accumulations of mass, either it's accumulations of pressure, either it's accumulations of heat or temperature. So it doesn't really matter. It has to have this capacity, which is defined by the volume, which is then defined by the size of the equipment, which is in this case d and then h, or d and then the height. Yeah. So the dimension of this equipment, we need to know this. And so also the dimension of this equipment, we need to know that. If we have a heat exchanger, we need to know the dimension of the heat exchanger. If we have a pump, so we need to know the dimension, or at least the head and then the pressure of the pump, the performance curve. So in dynamic, because you can see it's more complicated, we need to have more data, and then for dynamic to be able to run it smoothly, we have to be able to size this equipment accordingly. Or if we have already the size, and then we need to put that size into the simulations. So what we do, yeah, because this is just a simple case, we can just simply size this quickly, because HYSYS has provided the way for us to do so. We go to a rating, yeah, rating. And then the control valve, if you can still recall your process control lab, I'm not really sure if you can recall it, but in the in the process control lab, there is a module called control valve characteristics, where you learned about linear, quick opening, and equal percentage. So for the sake of this simplicity, we can just click linear. Yeah, you can Google yourself after these sessions about what this each of these characteristic, what does it mean. Yeah, we can check by default as linear. And then you know that, yeah, the flow rate coming in is 10,000, that one. The valve opening by default is 50, and then delta p is 1 bar. So this is the one that we put in, yeah, this is the one that we put in. So with this delta p, with this flow rate, we can then size the CV. So there are sizing method in ANSI or INSA, and then there's a manufacturer specific method. You can go to Fisher or whatever, and then there's a simple resistance equations like this. So V open square root delta P, so delta square root delta P, you can see, and then the K. So K is then my CV over here, and then the delta P, my CV and then delta P. So that's basically the simplest equation that you can have. we can just use the well-known, I mean the internationally accepted for practical applications here. You can just click size valve, and then you can see the CV. It was light blue, now it's darker blue, means it's we have it as an input. Yeah, it's 137.6. So you can leave it as it is, or you can just put it into a better nice, or if you can go to the catalog and then you can see what is then the correct CV. Is there any CV close to this number, or if the closest is then to 140 or 145, that's all up to you. So you can then put, like, for example, yeah, 145, and then at 145 it will then open 50%, for example, yeah, following this, and then you will get the CV. Okay, so we get the CV at one sorry, at, you can see here. So at 137.6 it will open at 50%, but then since we increase this a little bit, 140, so that means you will see later on that valve opening over here will then be reduced, yeah, in such a way that it will then match the CV value. So we are now sizing this, and then we have sized it accordingly, and then we go to the other valve as well, go to rating, and then the same, leave it as it is by default, yeah, for the time being, and then it is 41.58, and then we can just click the size, sorry, the CV sizing method using CV, and then we can click this, and then we have the 41.58, and then if you would like to see a nicer number, 42, for example. Okay, delta P 4 bar is the one that we have specified. The same goes with the valve 2. We size it as well with the CV, size it, and then yeah, I don't want to see 8.2, but I would like to see like 8, for example. Well, typically we put it like a higher number, but in this case I just like to show you what happens if we put it like a lower number. And then we hope to see that the pressure, the opening here will then be open slightly. Yeah, I mean higher than 50%. This one later on it will be then lower than 50%. This one will be lower than 50% because we increasing the size of the valve over here, there, just slightly. Okay, so we have sized these three valves, and then the remaining equipment to be sized is then this vessel. So yeah, just we can also quickly size it, yeah, or you can use your chemical engineering knowledge to size this equipment. Go to rating again. You could do quick size, because if you're so lazy to do so, quick size, and then if not, then you can have find it on the field what is then the diameter and the height, or you can you go to your textbook and then size it. Quick size, because we are so lazy. At the flat cylinder, yeah, just a flat. There's no sphere, there's no ellipsoidal head, there's no asymmetrical, it's just flat. It's a vertical, quick size, and we have diameter is 0.6, height is then 3. I don't like to see 0.6096. I just want to see like like a 1 meter in diameter, and then this is then 3.5, for example. So we size it now 3.5 meters height, and then 1 meter in diameter. So this is then the size of the this guy. Okay, yeah. Before we do dynamic, yeah, I can show you one thing that can help dynamic assistance. But before I show this to you, I will explain one more thing again here. Like I mentioned, that we have to specify this pressure, we have to specify this pressure, we have to specify this pressure, and then we'll see what the flow is going to be. Okay, so now if we specify it, and then we need to go to this stream, for example, and then we go to dynamic, and then we can see the dynamic specifications, either it is pressure specification or flow specifications, and both are active, and this is not allowed. We can only specify pressure or the flow, but in our case, because we would like to see in reality, it's going to be like well, most often than not, it's going to be like a pressure driven flow, because it's if the pressure is, there's no delta P, there's no flow. So we typically specify the pressure, hence in this particular case we just made this inactive. Okay, And the same goes with this streams, that these streams, for example, we go to dynamic, and then there is no tick. Yeah, it's not non-tick, because in this case we specify this. Basically, we already specify pressure and then the flow rate, and then when we go to dynamic, we say I just want to specify the pressure. Okay. But in this case, because we specified the pressure, sorry, the flow rate is coming from this stream 3, which is already calculated, and then this delta P across the valve, we define the delta P over here. So hence the flow rate here and then the pressure here is then going to be defined by this delta P and then the flow rate coming in. Yeah. So hence there is no tick. So the best way, well, a better way to do this is that we either delete this. Sorry, we need to know, yeah, it's a pressure is 5 bar, so we can either delete this, and then put a 5 bar over here, and then it will then be shown over here. So you can see this blue is 5 bar, and then it's automatically click active because we specify the pressure on the stream to be 5 bar, remember? Yeah, this valve. So we specify the pressure in stream 6 to be 5. Hence, when we open the stream 6, the 5 is thick. Okay, so we specify this pressure is active, not the flow rate but the pressure. The same goes with this guy. Yeah, if you go here and then if you directly tick this, I don't know if that can happen. It can happen, but this is not an input because this is not the blue, dark blue. So what we should do is then sorry, I'll just leave this open and then open the valve. um, it's a 5 bar as well, so I just remove this and then put a 5 bar over here or put 5 bar over there. It doesn't really matter. Okay, so far any questions?
Yes,
Yeah.
when you size the valve,
Yeah.
downstream of stream 3,
Yeah.
why do you choose CV, not CG, considering it is gas?
Doesn't matter. No, no. This the CG is not gas. Yeah. This is
Oh,
not
it's not
gas. Then this is not liquid V quid.
fluid.
No, no. This is not V quid, and this is not gas. It's just like this method. There's a CV and CG. I don't know what the CG is. I have to Google this myself. But CV is what we normally use. Because the
Oh,
equations,
okay.
typical equation is then if you Google if you Google this one, yeah. Valve flow coefficient, valve flow coefficients. Um, so you can see this flow coefficients, Wikipedia. So flow rate is Q, flow rate is in Q, and then CV multiplied by square root of delta P. Yeah. So Q equals to CV times square root of delta P. Can you follow if I put this over there? So we have flow rate equals to CV square root of delta T. So it's the same like in these equations. Flow rate equals to CV multiplied by delta P, square root of delta P. So that is what we call typically this CV, the flow coefficient. Basically, it's not CV quid. The same goes that with CG is the um, uh, is not the gas. Let's see what this CG is. Yeah, since you're asking, and I'm also curious. Sizing method, CG for ANSI flow of CG. Oh, this one in Emerson. Is there anything else? Atau CV blah 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 blah. This one, yeah, CV square root of delta P, and then what is then CG, yeah. Can go through this.
this one, universal gas sizing.
Universal gas sizing, CG. The problems in predicting critical flow with the CV-based equation led to separate gas sizing coefficient based on air flow rate flow test. Coefficient CG was developed experimentally for each type and size of valve to be critical. So we need to get this G somewhere experimentally. I don't know. And then well, basically you could use CG, CV, whatever, as long as you get that gas sizing coefficient. They put it to CG, and then S is steam sizing. I don't know. CV is liquid sizing. It doesn't really matter. I mean, what matters is that with whatever method that you select, either you want to use CV, CG, CL, CB, whatever, it has to be correctly sized. It has to be correctly sized. That's the number one. That's a fundamental issue that we have to say. For example, you put CG as well, and then this one CG, this then the current number. So your when we go to the catalog vendor, you go to Amazon, for example, and then we have to see the valve with this CG, the closest to the CG, like one size higher, for example. It cannot be too high because you will see there is a problem connected to it. You will see that later, but it cannot be too small because otherwise we'll have a high pressure drop. Yeah, one thing I have need to mention, the CVCG guy, whatever this is, the flow coefficients, if you can still recall the just use the simple explanation, the simplest, yeah, can see this, yeah. If the CV is high, you will have a higher flow rate, yes. And then if the CV is low, you will have a lower flow rate. So basically, yeah, if you have a higher flow rate, that means you need to have a bigger pipe, right? So you can have from that you can deduce that if we have a bigger pipe, that means the corresponding valve should be always also like a relatively bigger, right? Yeah or no? If you have a higher CV, that means you will have a higher Q, higher flow rate. If you have a higher flow rate, you must need a bigger pipe in diameter, right? If you have a bigger pipe in diameter, that means your CV, the corresponding CV, should also be like a relatively big. So that means the CV, the higher the CV, the bigger the size. Yeah, it means the smaller the CV, the smaller the size. Can you? So it has these connections with the size itself. Yeah, I don't know if it's the size of the your fist, or if it's the size of these your table. There is a valve like that. So depending on the if the valve is as big as the table, that means its CV is much bigger compared to the valve that we have in our bathroom. Can you follow? So
Yeah.
the valve that we have in our bathroom, they have all very small CV. But the valve that as big as our size, human size, there are valves like that. The CV is also very big. Can you follow? Yeah,
Yes.
that is the relations. So it's 42, and then if you, I don't have a feeling on if this 42, how big this is roughly. We need to go to the vendor catalog. But in any case, it's somewhere around this number. So okay, and then we have defined this, we have defined that, we have defined this, and then we can also ask this dynamic guy to call us, and then it says, well, it doesn't identify any problems. Yeah, say for example, you've got to specify this, for example, yeah, this is then non-active, and then we do it typically, this is no, and then we did what we just did. So it's a 4 bar, for example, and then you thought you have done everything, yeah, because it's this is a simple case, but in a more complicated case, well, we simply make mistakes. Human being make mistakes. And then, okay, I thought I did my best, and then I just click dynamic assistant for surety, and it give me this enable stream pressure specification. And then what the hell is this? Yeah, you could also click this make change, or you can go to stream because it says stream pressure. Go to streams, and then it says here stream 6 set pressure spec in this stream. Yeah, so we have to spec and we have to set pressure in this stream. So we go to this guy and we have to spec this. Press 5 5 5 5. I cannot do so. What is happening? Right, I have to press 5 and nothing happens. So in this case, okay, then I thought, okay, there should be something wrong here. uh, Press this, I cannot change anything, and then I go back to this parameter, and then apparently I can delete this, and then enter, and then put it over there, press, you can see it's there, and then it's over here, and then you go to dynamic. It is not active yet. Well, you thought that I have specified this, right? I mean, to analyze again, analyze again, analyze again. It keeps giving me this. I have to set pressure specifications. That means I can go back here. I ended up here in the cookie, and then I have said I've seen it here, 5 bar, but I still see ask me to set pressure spec, and then I go to dynamic, and then oh, I forgot to activate this, so I need to click this active, and then you analyze it again, and then it's gone. Okay. Say for example you forgot to spec this, um, this one, delete, delete, no, delete, delete. I don't know. I cannot delete this somehow. Anyhow, yeah, if you forgot to size this, and then it will give you I'll just kill this here, for example, for analyze again, and then it will give me this stream number 5. I have to set specifications, but in this case you can see stream flow spec, whatever. This is the most important one. We have to make it pressure spec, and then pressure flow spec, there's this it's a for LNG, it's a different one, so we rarely use this. Unknown sizes, for unknown sizes, volumes, and whatever. And then tray sections for the trays, and then others like component splitter, whatever it is that we will have in the case later on. Yeah. In this case, for example, I can just double click. Oh, I can then make changes. Sorry, click make changes, and then it will automatically be clicked over here. So that's basically how we set up. That makes sense. And analyze it can help us in this case. You can save steady state case and then click finish, and then the steady state case is then saved. So far, any questions?
No, I'm good.
No, you're good. Very good. So we could now go to dynamic mode. Yeah, enter or leave dynamic modes. I'm not really sure do I have to click this, or I can just go to integrator. Let's do this. Click it to the integrator. um, the unit is minutes, so it will be dt, sorry, dp, this guy, the dp over here, or whatever dt, that dt will be in minutes. Yeah, I just need to, before we will set up the controller next week. Yeah, I'll just need to show you the how it behaves in dynamic. So that delta t is then going to be in minutes. You can change it in seconds, minutes, hours, days, even years. Yeah. So we just leave it by default, and then it will start with the current time of 0. So you can specify any time, but we'll start normally at 0. And then acceleration is that this is then the delta. Yeah. Integration time step. So delta t is then 1 minute in this case. 1 minute. So if you want to have like 2 minutes, you can add 2 or 3 or 4. Yeah. So that means you are integrating every 1 minute. If you put 10, that means we are integrating every 10 minutes. That's and then end time is non-stop. It can run to will run to whenever. Um, Sorry, I was wrong. So the integration step is this guy. So it will then integrate for every delta t of 5 seconds, 0.5 seconds. So this was the delta t. This is an acceleration, so you can just speed up and slow down by multiplying this with with this guy. Real time, if we take this, that means 1 second in the simulations is 1 second in our real life here. 1 minute over here, that means 1 minute over there. So now it's 10:37. If we put this tick, and then if it's after 1 minute, this also goes by 1 minute, 10:38, something like that. Yeah, it will then run. If we take this, it will then run in the real time. Yeah, but if we don't take this, that means it will run the speed of the simulation runs depends on the speed the quality of the specifications of your laptop, of your computer. So now it's just just run this. Yeah, what's the big deal? Oh, I have to switch to dynamic. Yeah, I have to switch to dynamic, and then I'm running this. You can see it's nothing. It's changing a little bit flow rate over here, a little bit flow rate over there, or flow rate here, because we are changing the we change the file size, yeah, remember, and then hence the number is then a bit different, but in any case it's close to 10,000, close to 2,000, close to 7,000. So basically that's the case. It is running now. It's 1,766 minutes. And it is then you can see real-time factor, that means it's about thousands, yeah, thousands, or 3, 4, 5, 6. So it means it's running like a thousands time faster than reality than the current reality, because these are simple calculations basically. um, so it can calculate much faster. And then you can see, assume that this is your plant, and we have this boundary of the plant. Yeah, we have incoming F1, and then outgoing F6 and F5, stream 6 and stream 5. You can see there's no changing in the flow rate, right? But this is still in dynamic simulation, but the flow rate are constants. Yeah, the flow rates, incoming, outgoing, they are constants. Okay. Next week we will then open this. Let's see. In the separator, we can see the level. Let me see the dynamic. Hold up. No. Liquid level, it's 95% now, because of the mass balance that we are now giving into the the stream that we're giving into the vessel. Yeah, it's 95% now. Next week we'll learn on how to control this from 95% to, I don't know, 50%, 60%, 40%, I don't know. And then we'll control the pressure as well. Yeah, we'll try to control the liquid level. And then if we see the hold up, for example, is there any pressure? No, once pressure is 9 bar. Yeah, I want, for example, I want to increase this to sorry, to reduce this to 8 bar, for example, and let's see how we can do so next week. So far, do you have any questions? No? If no, then I'll see you next. I'll save this first, and then I'll see you next week, where we can then show you how to control the pressure, how to control the level, and how to control the flow rate, for example. And then if time permits, we can see how we can add another unit exchanger, for example, and we can control the temperature. And then we could also do like a cascade control. Yeah, let's see what happens. And then later on we will do like an event scheduler, for example. So at some time we can just sit and relax and then see. I mean, we can specify some scenarios via event scheduler. Yeah, next week or in the next 2 weeks. I don't know. Any questions so far?
I'm good.
No? Okay, then I'll see you next week. Yeah, other questions? No questions? No questions. If there's no questions, then good. Thank you, and have a nice weekend. And I'll see you next week. Bye bye.
Right. See you too, doctor. Thank you.
Yeah, thank you. Bye.